The Lockheed P-38 Lightning arrived in the European theater in 1942 with a striking appearance and formidable specifications. Twin engine, twin boom, heavily armed. It was faster than most fighters in service. It carried more firepower. It had range that single-engine fighters could not match. On paper, it was exactly what the 8th Air Force needed for long-range escort missions deep into Germany. Commanders expected it to dominate. Pilots expected it to protect the bombers and outfight the Luftwaffe. But within weeks of entering combat over Europe, the P-38 was failing. Not occasionally. Systematically. Pilots reported engine failures at altitude. They reported cockpit temperatures that made sustained flight unbearable. They reported that German fighters were outmaneuvering them. Loss rates climbed. Confidence eroded. By early 1944, the aircraft that was supposed to win air superiority was being withdrawn from the theater. This was not a failure of courage or tactics. This was a failure of engineering assumptions that testing had not exposed and combat could not forgive. The P-38 was designed as a high-altitude interceptor. Lockheed engineers configured it with two Allison V-1710 engines, each driving a propeller that rotated in opposite directions to cancel torque. This eliminated the handling problems common in single-engine fighters. The twin-boom layout placed the cockpit in a central nacelle, with the tail surfaces connecting the booms. The engines were turbocharged, allowing the aircraft to maintain power at altitudes above 25,000 feet. Armament was concentrated in the nose, one 29mm cannon and four 50 caliber machine guns, all firing forward without the synchronization problems of guns firing through a propeller arc. The design was unconventional, but it was coherent. The Army Air Forces wanted the P-38 because existing fighters lacked the range to escort bombers to Germany and back. The P-51 Mustang was not yet available in numbers, and its Merlin engine was still being integrated. The P-47 Thunderbolt had range, but it was not yet fully operational. The P-38 was in production. It was available, and it promised the performance needed for deep penetration missions. Commanders believed it would solve the escort problem. They believed the twin-engine design would provide redundancy and safety. They believed the turbochargers would allow it to fight effectively at the altitudes where bomber formations operated. These beliefs were based on test data and engineering projections. They were not based on combat in the European winter. Lockheed had tested the P-38 extensively in California. It performed well. It was fast, maneuverable, and reliable in the controlled environment of the test program. The Army conducted its own evaluations and found the aircraft acceptable. Orders were placed. Production ramped up. Pilots transitioned from single-engine types and adapted to the twin-engine configuration. The aircraft was declared ready for combat, but the testing had not replicated the conditions the P-38 would face over Germany. The European theater demanded long missions at high altitude in winter conditions. Bomber formations operated between 25,000 and 30,000 feet. Escort fighters had to maintain position with the bombers for hours. They had to be ready to engage enemy fighters at any moment. And they had to do all of this in temperatures that routinely dropped to -40 degrees Fahrenheit or lower. These conditions were not part of the California test program. They were not anticipated by the engineers who designed the cooling systems, the cockpit heating, and the engine management protocols. The operational environment was fundamentally different from the test environment. Pilots trained in the United States under temperate conditions. They learned to manage the engines, to coordinate throttle movements between the two power plants, to handle asymmetric thrust if one engine failed. They practiced gunnery and formation flying, but they did not practice sustained flight at extreme altitude in freezing conditions while wearing bulky flight gear and oxygen masks. They did not practice combat maneuvering when the cockpit was so cold that instruments frosted over and fingers lost feeling. Training validated that pilots could fly the aircraft. It did not validate that they could fight in it. The P-38 was deployed to England and North Africa in late 1942. In North Africa, it performed adequately. Missions were shorter. Altitudes were lower. Temperatures were warmer. The aircraft's strengths, firepower, range, speed, were useful. Its weaknesses were not yet apparent. But in Europe, the environment was unforgiving. Missions lasted 4 to 5 hours. Altitudes were extreme. Temperatures were brutal. And the Luftwaffe was experienced, well equipped, and aggressive. The P-38 was about to be tested in ways that its designers had not foreseen. The first large-scale escort missions over Germany in late 1943 revealed immediate problems. Pilots reported that the cockpit heating system was inadequate. At 25,000 feet, outside air temperatures were well below zero. The heater, which drew warm air from the engines, could not maintain a comfortable temperature in the cockpit. Pilots flew missions in extreme cold. Their hands and feet went numb. Instruments frosted, canopies fogged. Some pilots suffered frostbite. This was not a minor discomfort. It was a tactical disadvantage. A pilot who could not feel his controls, who could not see his instruments clearly, was a pilot who could not fight effectively. Engine failures became common. The Allison V-1710, when operated at high power settings in extreme cold, experienced coolant system problems. The turbochargers, which were critical to maintaining power at altitude, were sensitive to temperature. In the cold oil in the turbocharger control system thickened. Response times increased. Pilots found that rapid throttle movements caused turbocharger malfunctions. The turbocharger would overboost, pushing manifold pressure beyond safe limits, or it would fail to boost at all, causing a sudden loss of power. Either condition was dangerous. Overboost could destroy the engine. Loss of boost meant the aircraft could not maintain altitude or speed. And at high altitude, over enemy territory, either failure was potentially fatal. The coolant system was another critical weakness. The Allison engines used liquid cooling. Radiators were located in the wing leading edges. In extreme cold, coolant temperatures dropped rapidly when power was reduced. If a pilot throttled back during descent or while maneuvering, the coolant could cool too quickly, thickening and reducing flow. This led to localized hot spots in the engine and potential failure. Pilots learned they had to manage power settings carefully, keeping engines warm even when less power was needed. But in combat, where throttle movements were constant and rapid, this was difficult. Engine failures occurred without warning. Pilots found themselves flying on one engine, or neither, over hostile territory with no chance of reaching friendly lines. The P-38's handling characteristics at high altitude compounded these problems. The aircraft was heavy. It had high wing loading. At altitude, where air density was low, control response was sluggish. Pilots found that the aircraft did not turn as tightly as German fighters. The Bf-109 and F-190 could out-turn the P-38 in sustained engagements. They could also outdive it. The P-38's compressibility characteristics were problematic. At high speed in a dive, the aircraft would become uncontrollable. The controls would lock. The nose would pitch down. Recovery required slowing the aircraft, but slowing in a dive while under attack was not always possible. Pilots learned to avoid high-speed dives, which meant they could not always escape or pursue. This was a significant tactical limitation. The turbocharger system, when it worked, was complex to operate. Each engine had its own turbocharger, controlled by the pilot. The pilot had to coordinate throttle, turbocharger, and propeller pitch for both engines simultaneously. In combat, this required attention that should have been focused on situational awareness and gunnery. Pilots reported that managing the engines was a full-time task, leaving little capacity for fighting. Some pilots simplified the problem by keeping the turbochargers at fixed settings, but this sacrificed performance. The aircraft was too complex for the environment in which was being used. Testing had not exposed these failures because test flights were conducted under benign conditions. Test pilots flew at moderate altitudes, in moderate temperatures, for short durations. They did not fly 4-hour missions at 30,000 feet in sub-zero temperatures while under fire. They did not experience the cumulative effects of cold, fatigue, and combat stress. They did not discover that the cockpit heater was inadequate until pilots flew combat missions in winter. They did not discover that the coolant system could not handle rapid power changes until pilots maneuvered in combat. Testing validated the design under ideal conditions. Combat revealed that ideal conditions did not exist. The interaction between systems created additional problems. Cold affected not just the engines, but the hydraulics, the electrical systems, and the control surfaces. Hydraulic fluid thickened, reducing responsiveness. Electrical systems, stressed by heaters and other equipment, sometimes failed. Control cables contracted in the cold, changing the feel and response of the aircraft. Pilots reported that the aircraft they flew in combat felt different from the aircraft they had trained on. It was heavier, slower, less responsive. This was not imagination. This was the cumulative effect of environmental stress on a design that had not been optimized for those conditions. Pilots began to avoid the P-38 when they could. Experienced pilots requested transfers to P-47 or P-51 units. New pilots assigned to P-38 squadrons faced the aircraft with apprehension. A maintenance crews worked constantly to address the problems. But many of the failures were design-related and could not be fixed in the field. Engines were replaced. Coolant systems were modified. Cockpit heaters were supplemented with additional insulation and electric heating elements. These were stopgap measures. They improved conditions but did not solve the underlying problems. Commanders recognized that the P-38 was not performing as expected. Loss rates were higher than acceptable. Mission effectiveness was compromised. Some units achieved success with the P-38, but these were exceptions. The aircraft required skilled pilots who understood its limitations and could work around them. It required careful mission planning to avoid the worst conditions. It required extensive maintenance that other fighters did not. The operational burden was too high for the results achieved. By early 1944, the decision was made to phase out the P-38 from the European theater. It was not officially withdrawn, but it was reassigned to secondary roles. New P-38 deliveries went to the Mediterranean and Pacific theaters, where conditions were less demanding. In Europe, P-51 Mustangs replaced the P-38 in escort missions. The Mustang, with its Merlin engine, superior high-altitude performance, and simpler cockpit, proved far more effective. The transition was quiet. There was no public acknowledgement that the P-38 had failed. It simply disappeared from the order of battle. In the Pacific, the P-38 performed better. Missions were flown at lower altitudes. Temperatures were warmer. The aircraft's range and firepower were valuable. Japanese fighters, while maneuverable, were lightly built and vulnerable to the P-38's concentrated nose armament. The problems that crippled the P-38 in Europe were less severe in the Pacific. The aircraft found a role where its strengths mattered, and its weaknesses were manageable. But this was an admission that the original design assumptions had been wrong. The P-38 was supposed to be a universal fighter. It was not. It was effective only in specific conditions. Late war modifications addressed some of the P-38's problems. The P-38J and P-38L models had improved cockpit heating, revised coolant systems, and better turbocharger controls. These versions were more reliable, but they came too late for the European campaign. The lessons learned from the P-38's failures informed the design of later aircraft, but they did not redeem the aircraft itself. The P-38 remained a machine that had promised more than it could deliver under the conditions that mattered most. The P-38 Lightning was not a bad aircraft. It was an aircraft designed for conditions that did not match the operational environment it was forced into. The engineering was sound within the assumptions that guided it. But those assumptions, that testing in California could predict performance over Germany, that systems adequate in moderate conditions would remain adequate in extreme conditions, that pilots could manage complexity while under fire, were flawed. The gap between expectation and reality was bridged not by redesign, but by operational adjustment. The aircraft was moved to theaters where it could succeed. In Europe, where it could not, it was quietly replaced. The shock to commanders was not that the aircraft failed. It was that the failure was so complete, so systemic, and so resistant to correction. The P-38 was rushed into combat because it was needed. It failed because it was not ready. That distinction mattered.